Happy to introduce Lechi Liu. Did I pronounce that right?
Yes, that's right.
Okay. She's a new professor in the business school. Got her PhD in the machine learning department at CMU and worked with Zach Lipton, and then was at Princeton Language and Intelligence, Sanjeev and Danshi's center, and studies large language models and machine learning for different modalities, including health. So just started, new professor, so we're happy to have her here and excited for your talk.
Yeah, thank you, Adam. Thanks for the introduction. And since we have a small audience, so yeah, please be interactive. If you have any questions, thoughts, please feel free to raise it. So we're gonna spend 2 to 3 minutes talking about just primer on language model and how these models are trained. And then after that, we're gonna go into how do we build personalized language model under the RLHF framework. And then we're gonna move to discuss whether there are some common pitfalls of these current language model alignment algorithms. And then in the end, since I'm new here, I'm just gonna describe a little bit about our lab and what some sample research projects we're looking at. I'm very happy to chat about research, so feel free to contact me. So language models are just next token predictors. So for example, given a sequence, I am in Washington, DC to attend the language model will output the probability of next token. So the probability of workshop could be 0.1, conference could be 0.05, and cherry is very low because it's a grammatically incorrect answer. So large language models are just language models that are large in 2 ways. First, it's trained on a large set of data. In particular, a lot of data scraped from the web, from GitHub, Wikipedia, archive, and all other places you can think of. And then it's also large in terms of the size of its parameter. So I remember at the beginning of my PhD, which is 2017, even like couple hundred million, actually even couple million parameter models are considered to be large. And now we're entering like thousands of billions of parameters. So yeah, we're in the large language model era. So the training of these large language models can, at a very high level, be divided into 2 stages, although right now, the stage can be even more nuanced. But at the very high level, there's this pre-training stage where we get a lot of web data, and then we're just training the model to predict the next token, trying to maximize the likelihood of the next token. So why is this a good idea? It turns out that these next token prediction tasks can teach the model to learn multiple skills. For example, when we are predicting, we are gathering here to discuss or discussing, the model is learning something about grammar. By predicting the correct one, the model is learning something about grammar. So in the second example, Washington, DC is the capital of America or France. By putting probability on America higher than probability for France conditioned upon the prior sequence, the model is learning something about factual knowledge. Third example, compared to a dog, a cat is commonly bigger or smaller. If it predicts smaller, then the model, in some sense, gets some common sense while learning to predict this next token. And then lastly, the sum of 13 and 14 is 27 or 28. So by predicting probability of 27 close to 1, then the model is able to learn some mathematical skills. So in general, this next token prediction is a very powerful and easy approach to teach models to obtain multiple skills. But next token prediction is not enough. So for example, when we are given this sequence, explain the theory of gravity to a 6-year-old in a few sentences, with just pre-trained model, the model is just gonna continue completing the sentence. For example, it's gonna just continue saying that explain the theory of relativity to a 6-year-old in a few sentences, explain the Big Bang theory to a 6-year-old. This is not really following the instruction that the user have given to the language model. So just by predicting the next token, the model is not learning to understand user intent and follow instructions. So to resolve this issue, then people started to look into some post-training what used to be called fine-tuning approaches for these large language models. So in particular, in this phase, the data set is a lot smaller. And in general, the most popular pipeline for this is what's called reinforcement learning from human feedback. And within RLHF, there's 2 stages. The first stage is called supervised fine-tuning, where we're given demonstration data, meaning that there's a given prompt, like an instruction, and then a demonstration of how to follow that instruction, and the model is still doing next token prediction. So conditioned upon the prompt, and then the generated token so far is still trying to maximize likelihood of the next token in the demonstration data. And then there's the second stage, which is the so-called RL stage. And then here we're given preference data. So there's a prompt, the instruction the person is giving, and then there's 2 responses, one being the chosen response, the other being the rejected response. So YW here is the chosen response, meaning it's a response that probably followed the instruction better, and then YL is the rejected response. And these labels are provided by humans, and now sometimes also provided by other language models or even verifiers. Okay, so yeah, this is the general RLHF pipeline.
Excuse me.
Yes, please.
In the supervised fine-tuning, is there also teacher forcing that happens there?
Teacher forcing?
Yeah.
Yes. Yeah, it's the same. It's conditioned upon the generated, it's exactly conditioned upon the demonstration data so far, and then maximize the likelihood of the next token. Yeah. Any other questions?
Does that not hamper the performance during inference? Because during inference it has to generate given what it has
Generated so
already
far?
generated.
Yeah. So because we don't have the training signal for that, ideally I agree. It would be nice if we can just know that condition upon what I generated so far, what's the best next token. But we don't have that data. So in SFT, it's still doing condition upon what's in my demonstration data so far, and then predict the next token.
Like there are some papers that show that if you do teacher forcing during training.
So yeah, I know what you're referring to, that paper.
What's
like
teacher force?
So yeah, I can explain. So in generation, when we generate the next token, we're conditioned upon the prompt and the generated content so far, and predict the next token. Versus teacher forcing would be given demonstration data, we condition upon the entire offline data and try to maximize the probability of the next token.
Like you use the true output itself. So during training, you have the true y also. So you take the prompt and the y that is true, like in the training data itself, to generate or to maximize the likelihood of the next generated token. While during inference, what happens is there's no true y available now. So it uses the self-generated y to only predict the next token.
So I agree, it's not ideal, but there is some practical obstacle to that. Actually, if you come up with good algorithm that uses generated data to supervise, then that would be the best. But the practical reason is because when we do generation, it's autoregressive. It will be very slow. But then when we do these training, we can process all the tokens so far at the particular time step. We can process all the tokens and then predict the probability at position 1, 2, 3, 4, 5, 6 at the same time. So we can do the training very fast. Okay, any other questions? Okay, so just dive slightly deeper into the training objective for the RLHF. So we know that, there's this SFT stage that try to predict, maximize the probability of the next token. There's this reward learning stage that takes in preference data and try to learn something about this preference, which use a reward to summarize. And then given that reward model, the third step is to run some kind of policy gradients. In particular, a lot of time it's PPO to optimize for that reward. So instead of this 3-stage approach, or I guess like in particular for the RL part, it's 2-stage, people have come up with something called direct preference optimization. It's still the goal is to maximize some kind of reward subject to the KL divergence between our learned policy or learned language model and then the reference policy, which most of the time is the SFT learned policy. And then it turns out that this is a common contextual bandit problem, and there's a closed form for the policy. In particular, it gives this form. So the probability of a response given a prompt is equal to 1 over a partition function on x. This does not depend on the response y, multiply my reference model probability times exponential to 1 over beta times the reward model. So this is a contextual bandit problem, just to be clear, because the context in this case is the prompt x, and then the arm we're pulling would be y, the responses. So these are like very large scale contextual bandit problem, because the response space is v to the power t, where v is the number of vocaps and t would be like the maximum length of the generation. So once one realizes, okay, there's this closed form, we can plug this form back to the reward model learning objective, and then get something called a direct preference optimization loss of this form. So it's basically a loss that depends on the log probability of a chosen response and the log probability of a rejected response. And it's trying to maximize the margin between some function of the chosen response log probability and some function of the rejected response probability. And since then, there's just a lot of paper coming out talking about different preference optimization objectives that take similar form, which by that I mean like some function of the log probability of the chosen response and then some function of the log probability of the rejected response, and try to look at the margin between the two. So what's missing here? Which enters the first topic we're going to discuss, which is personalization. So when someone asks, okay, explain to me what is ChatGPT, there are different way we may expect it to answer, but then without knowing explicitly who these users are and what their prior dialogue with ChatGPT is, it would just reply the generic one, which is ChatGPT is a conversational AI. However, behind this query, this prompt, there could be different person. It could be like a old grandpa. In that case, then we may expect the response to be, ChatGPT is a computer program that does certain things. Versus, it could be just a kid asking what is ChatGPT. Then ChatGPT in this case ideally should reply as, it's like a super smart robot in language that the kid understands. And then in the third case, if we have someone like us who have technological background and in this, then they can start to say, okay, ChatGPT is a conversational AI that does certain things. But, and in particular, this kind of personalization capability will be useful in different application domains for these models. Like, for example, healthcare. If we're trying to build a chatbot system to answer people's queries about things, it would be better to understand what the communication style, for example, the different users prefer. So now the question becomes, how do we efficiently build personalized language models with human feedback, with just preference data? So any question so far about the goal of this work? Okay, so if not, then hopefully I convinced you it's an important problem to tackle, building personalized language model. And then to solve this, let's delve slightly deeper into the reward learning step. So in this reward learning step, we are given a data set consists of a prompt, and then a chosen response, YIW, and a rejected response, YIL. So W is winning, L is lose. So in this reward learning step, the main assumption is the Bradley-Terry model, which is the probability of the chosen response preferred over the rejected response follow this form. It should equal to like the sigmoid of the reward of the chosen response under the prompt minus the reward of the rejected response under the prompt. And then under this Bradley-Terry model, what reward learning is doing is just trying to maximize the likelihood of foreseeing data under this reward model. Any question about this?
Is this symbol mean?
This one?
No, the greater than.
Oh, preferred over.
Preferred. Oh.
Yeah. Okay, so what's missing here in the personalization setting is behind these preference data is different user. So for example, we may have user annotation index. And then the implicit assumption here is that there's also a preference uniformity that's being assumed, which says basically conditioned upon the prompt and the user index, the preference of that user is the same as if there were no user index assumed, conditioned upon. So what are some consequences of this? So first, I hope I have convinced you so far that human preferences are diverse and subjective. So there is no just one uniformly correct preference. And second, under this preference uniformity assumption, the model we're going to learn will be of a majority voting kind. So what do I mean by that? So suppose that I'm getting human feedback on a prompt I like, and then the feedback is on 2 tokens. One is dog, one is cat. And 2 of the users said, okay, I prefer dog, and then 1 of the users said, I prefer cat. So under this training objective, what we're going to learn is that the probability of dog preferred over cat conditioned upon I like is 2/3. And then the generated text in this case, if we assume that the model is doing greedy decoding, meaning that it will just output the most likely token, then it will just be I like dog. Okay. So the third consequence is that suppose there's a mixture of preference, so we have a minority group and a majority group, then the deviance between the minority group's preference and then the assumed uniform preference is going to be higher than the deviance between the majority group preference and the assumed uniform preference. And in particular, the difference between these 2 deviants will increase as the majority group size increases. So these are very direct implications and calculations. Okay, so now that we know that there are bad consequences of assuming preference uniformity, and there's also practical needs for building personalized language model. So how do we do that? So it turns out that we come up with a very simple approach, which works actually very well, which I'm happy about, because a lot of times we come up with sophisticated approach, which may not necessarily work as well without a lot of tweaks. And in this case, it's the opposite. So what we did is we learned a user model that maps the user information, and most of the case is just a user identifier, to a user embedding that serves as a soft prompt, putting in front of the embedding of the token, the prompt tokens. So in particular, this works as the following. So this is the word token embedding of the reference model that we're dealing with. So basically, when we are given a lot of prompt, we need to tokenize it. And once we tokenize it in transformers, we need to map the token to a particular embedding. So this is the word token embedding step. So after we get this embedding, we prepend this with a user embedding that we learned later. And then this way, when we generate the response, it's always conditioned upon both the prompt, as well as the information about the user. Any question about this? Yes, please.
Do you have a lot of preferences from the same user?
In some setting, yes, but not all the settings. So in particular, for the last experiment I'm going to show, we only have, I think, maybe 10 dialogue annotation, 5 to 10 dialogue annotation per user.
So then the user embedding has to be correspondingly very small.
Oh yes, so we can specify the number of user tokens.
Yeah.
Yeah, and then the embedding.
No, the thing is, even if you have 1 token,
Yeah.
that's a lot of dimension,
Yes.
right? So, if I only have if I as a user gave only 5 preferences,
Yeah.
then I cannot support more than a 5-dimension, 5 scalar numbers representing me.
I
Even
agree
a
with.
single dimension would overfit the thing, right? Like even a single token would overfit me.
Yeah, I agree with you, but one can argue that in general, for any neural network, it's an unidentifiable problem, and there are so many ways to overfit the data. But in this case, the number of the token embedding size for user is the same as the token embedding size for each vocabulary. And then it just learned very well. Oh, yes, please, sorry.
How is the user model trained?
We will talk about this in a bit. Yes, the loss for that. Any other questions? Okay. So in our experiment, for example, the user embedding size would be like 764, which is common in a lot of the a lot of the open weight models that people are interested in.
Sorry,
Yeah.
the 764 is same as the vocab embedding size, right?
Yes, it's the same. So that's what, so yeah, the practical reason is that then it's easy to just concatenate this and then do the forward pass as it would behave. Okay, so what is a user model? How do we learn this? So there are many, so user model is learnable and there are many ways we can define it. So for example, if we just have a user model that output nothing, then we get back to the traditional base language model. And then there are another way to do this, which is if we have a user embedding table that's of size m+1, where m is the number of unique users we've seen so far, and then 1 is just the embedding we learned for any generic user that we do not know their index, then this is an embedding table, so user model can be an embedding table. And then, sorry, n is actually the dimension that Jay was saying. Sujay was saying, sorry. Okay, and then the other way is suppose I have just a lot of user and then my embedding table is gonna be huge, then maybe we can do some efficient, like a better way to approximate this. So in particular, we consider a user model that's just a multiplication between two embedding tables, one of the size n+1 times k, the other one of the size k plus n, where k is the number of clusters. So in this way, the interpretation is that the user embedding is a weighted combination of k basis vectors. Okay, so this can efficiently reduce the number of trainable parameter in our case. Finally, I just want to say that we are just giving examples of user models, and if you have better user models, you can always use that. Any question about this? So once we have the user model defined, the question becomes, how do we learn this? So recall that the kind of data we're given is a prompt and a preferred response, a dispreferred response, and a user identifier. So the laws we're gonna use to learn these user model as well as the language model is a weighted combination of a DPO loss for the user-specific case, so condition upon U, and then a user loss where we don't know about the user index. So condition upon this U0, which recall that I mentioned in our embedding table, we have an embedding for users we do not know. Okay. So it's actually very simple. And then the good thing about this is it's adaptable to any PO algorithms. So suppose today I don't want to do DPO, I want to do personalized IPO or personalized SimPO. Then instead of doing this user-specific loss and user-agnostic loss using the original DPO form, we can replace this by having the user-specific IPO loss and the user-agnostic IPO loss, and then do the same weighted combination, and we can learn the user model the same way. Any question about this? Okay.
How do you select alpha?
Sorry?
How do you select the alpha parameter?
Alpha? Oh, we just put 0.5. Yeah, we didn't really play with it much. Yes, please.
So you do this during training,
Yes.
but then during inference, there is no user.
Oh, inference, we do have user ID. So inference, either we have the user ID or we don't know about
Yeah,
this.
but what if it's a new user?
Yeah, we have, I should mention that this could be the user ID or some textual information about user. So if we don't have the user ID, then it's, in this case, we also learn the separate embedding for people who don't know anything, but only some textual information or without the textual information.
Okay, so you're learning a model which like previously the model would give an X, predicted reward or whatever, user reward for Y. Now we need X and U as an input.
Oh, so it can be U, can be empty. So this U0 case, so we learned a separate embedding for people we don't know anything about. But it was still, yes, conditioned upon that embedding, but we don't need to know any information about that user.
So U0 is an embedding that just captures preferences for which you do not have user labels.
Yes. In some sense, it's like a general preference. And then we will see actually in the experimental result, the performance for these users are similar to vanilla RLHF. So without knowing their user index.
And what does it do to like have a weighted combination of these two losses? Like how is the user agnostic loss affecting the user specific loss?
So the reason why we had both is mainly because we want to account for users we don't know. So if all of the users are known to us, then this would be enough. And this is mainly for, the first thing is accounting for unknown users. The second thing is we also tried a user model where the user embedding is the sum between the generic user embedding and some deviation. So I didn't go into details about this. So in this cluster-based model, the embedding of the user actually is the generic user embedding plus the weighted combination of the bases. So this weight is actually learning a deviance between the generic user embedding and the individualized user embedding. So in some sense, this generic user embedding can also serve as a regularization so that, it wouldn't, individualized preference wouldn't deviate from it too much. Yes, please.
Just to confirm, is the user model trained together with the machine model?
Yes, it's not trained separately. Okay, so how is the performance of the model? We tried 3 settings. The first one being an entirely controlled setting where we kind of know what the optimal behavior of the language model is, because without using a controlled setting, most of the time people just evaluate the performance of these language models using win rates, which sometimes can be unreliable. So in this case, we are using the TLDR dataset where the X would be the Reddit post, and then Y1 and Y2 are summaries of these two summaries of the same Reddit post. And then there's a worker ID who have labeled which one is preferred over the other. And this dataset is actually the first RLHF dataset released by OpenAI 5 years ago. So we simulate the user preference in this case, where 70% of the worker always prefer the longer response, and 30% of the user always prefer the shorter response. So the shorter response would be the minority group. So in this case, we know that for minority users, the probability of short preferred over long is 1. So that implies, the reward difference between a short response and the long response should go to infinity. So in this case, the optimal behavior for the minority user, the optimal language model behavior for the minority model would be to generate a response with length 0. Any question about this? Okay. So just a quick discussion about the training setup. We have 10 workers. We find the top 10 workers. We also tried the same experiment on top 40 workers. The behavior is similar, but for now, let's just say there are top 10 workers in our training data set. And then in the test set, we have the test split for this top 10 workers, as well as the other unseen workers. So the accuracy we're gonna look at, the first one, the evaluation metric would be the response length. Like I discussed before, we can use this to inspect whether the model was able to learn like these conflicting preferences. And then we have also looked at the accuracy for our training users. So in some sense, it's like in distribution performance, and then the accuracy of the generic user, which means we do not know this user in our training data set. How does it perform for that user? And then finally, the accuracy on average for the majority and the minority group. So this is the first plot, and I think we can just focus on this part. This is the same plot, but then for the top 40 user case. So in this case, first, we can observe that for the generic user, this is for the unseen user, our model, these red and blue bars, the solid bars, performing similar to the vanilla RLHF performance. So this is just a, yes.
Just a question about your setting.
Yes.
So you told us about how the preferences are in the synthetic setting, but what is the data? Is that text?
Yeah, it's text. So it's summary of the Reddit post, the responses.
Right, and so maybe can you remind us like how are these synthetic things made based on the text?
Oh, so it's just whenever there is a longer, so for some users, they will always prefer the longer summary. Some users, they will always prefer the shorter summary.
Okay, that's what you mean by synthetic user. It's like first you have this text, then you just make synthetic user which is like I like long text, and another one which is like I like short text.
Yes, that's right. Right. Okay. Yeah. So generic user, it performs similar to vanilla RLHF. So this is saying that without knowing any information, we're gonna do no worse than traditional method. And then let's look at the majority and minority average performance. So it turns out that especially for minority users, our model's accuracy is a lot higher compared to the vanilla RLHF, which is kind of expected. And what's very surprising to us, which is great, is we also look at the generation length. So in this case, generation length is equivalent to generation quality. It turns out that, so for the minority users, they're like 4, 5, 6, the generation length is just 0. So the model was able to just output an end of sentence token. Versus for the majority users, it was still trying to output like some words and trying to maximize the length. Yes, please. Oh no, okay. Yeah. Okay, yes, please.
First, have you tried the setting in which the minority, they don't always prefer the shorter one, but they prefer with, say, probably 90%.
Yeah, we tried that actually. So it would be like something like this. So it would still prefer like, yeah, generate some shorter one, but not all the time, but not to 0. Yeah.
It's like,
Yes.
sorry.
Oh, my question is, since you know the types of like users, you know their preferences, have you tried to compare your method with just pure prompting?
Yes, that's a good question. So later on, so in the next experiment, we did that. We did SFT with the ground truth preference prompting, and then we also outperformed that. In this case, we didn't try that. And I doubt it would generate end of sentence token though, even if it says I prefer shorter response.
Okay.
Yeah. Yes, please.
The variable U, is it the user ID or is it the user's preference? Like, is it some text or is it just
In this case, it's just the ID. So later on, we have cases where we use the preference as well. Yeah. So in some sense, there's no way the model is able to from the training data summarize and then got the preference. It has to be learned throughout this process. Okay. So the second setting is this semi-synthetic setting. There's a data set called Personalized Soups from UW. There they have 6 different user preference profiles, and then the label is given by role-play GPT-4. So here are the 6 profiles. So you can read this. The first one being explain things that's easily understood by elementary school student. And the second one is the style should be appropriate for a PhD student. Third one is being concise. Fourth one is being very, very informative. Fifth one being friendly, and the last one being unfriendly responses. So they created these preference profiles and these prompts, and then asked GPT-4 to role play with this preference profile, and then label alpaca evals prompts and generations using this. I should mention that during the PDBO training, so during the training of our algorithm, we do not know any of these preference prompts. All we know is still just the instruction the person used, the preferred response, dispreferred response, and then the user ID, so being 1 through 6. So in this case, how can we actually evaluate the performance of the model? Turns out that what people decided upon is something called win rate, which is, suppose I have my model and another competitor model, and I do the generation for the same prompt. I get 2 responses, and I ask some ground truth labeler to tell me which one is preferred over the other. So in this case, it still kind of makes sense because the labeler themselves are GPT-4 in the training data. So we use the same labeler that generated the training data to evaluate our model. And then, so for win rate, then about 50% would be good because that means more than half of the time when our model is preferred over another model's response. So we compared against 3 competitors. The first one is just vanilla SFT, so no preference training. And then you can see that across all users, we got preferred better. The second one being vanilla DPO, let's just consider this as the vanilla RLHF pipeline. And in this case, we also performed better overwhelmingly. The last one is actually the baseline you were considering, which is we have SFT model prompt with the exact preference prompt that we went through just now. Basically, it's a role-played SFT model that have ground truth preference. So this is a super, super strong competitor. And even in this case, our model was able to compete against it most of the time, except user 4, which is always being super informative. I don't entirely know why, but it's close to 50. So it's probably just a hard preference to learn. Yes, please.
Are these like real people with complicated preferences?
So no, these are the role-played ones, these 6 profiles. Okay, last one, a complicated real-world setting. This is the largest preference data set, which was collected last year. It's called PRISM, and I actually just know that they won the Best Paper Award in data set and benchmark track at Europe. So they have 1,500 participants from 75 countries, 8,000 dialogues, and then the label is per turn. So for each turn of the dialogue, someone come in, not someone, like the user who interact with this chatbot is going to provide a preference label. So we tested our method on PRISM and then compared it against the vanilla DPO as well as the chosen response in that data set. And then our win rate, which is here, is also higher. So more than 50% of the time we're preferred over that. But this may not necessarily give you anything beyond just numbers. So we actually found an example of what our method is generating. So in this data collection process, they collected something called system string, which actually describes users' explicit expectation about what they want the model to behave like. And this is not given to our model. And so in this case, this person put drinking alcohol is not a sin. So this is in a big dialogue, and then it's one of the terms the person said, drinking alcohol is not a sin. And then in their system prompt, when they reflect back, they want the model to behave like a friendly human friend. And then we have the response given by PDPO, vanilla DPO algorithm, as well as the chosen response in this data set. So what we see is that in our case, it's actually acting like a friend. It says, it's interesting to note that societal views on this subject can vary greatly. Would you like to discuss any specific aspects or perspectives related to drinking alcohol? Versus in vanilla RLHF, the model just directly changed the topic to some topics in previous turn of the same dialogue. It says that you don't have strong feelings against drinking alcohol, you might enjoy it or see no issue with it. Is there anything else you'd like to discuss? Here are some suggestions based on your preferences. So this is related to what they have discussed before. And then in the chosen response, in that data set, it says, but it's important to drink responsibly, basically giving some preachy talk about drinking. So you can see that just in this small example, PDPO was able to learn the implicit user preference that was not specified in the data set at all. Okay, any question about this? And then last note about efficiency. So our user model is much, much, much smaller than a trainable parameter for the base model. This is not the entire base model parameter, I mean the LoRa adapter parameters for the base model. So in particular, in the PRISM case, it's 10x smaller than the LoRa adapter for the base language models. Versus existing approach for training these personalized models require us to train multiple versions of a base language model. So it will be multiples of the LoRa, the number of parameters for the LoRa adapters for these language models. Yes.
Was your base model a Llama model?
Yes, it's a Llama 3 8B model.
Okay, and then for every user, you had the user tokens. But did you also have LoRa adapters, like a per user LoRa adapter, or did you have a single LoRa adapter?
A single LoRa adapter.
So a single LoRa adapter for the base model, and
Yes.
per user tokens. Like
Yes.
Per user prefix tuning and LoRa for the main.
Yes, that's right.
And so, what if you did not do the LoRa for the main one and just did per user DPO?
So we tried that. It's not performing as well, but it's still able to do relatively well, but not as well as the one with LoRa adapter.
Yes, but I mean, right, because the thing with LoRa is that you might degrade the base model on other tasks.
Oh, yeah.
I mean, this
Okay.
is not like this is just a separate
Yeah.
problem, right? And,
Yeah.
While it seems for you, if you just do TPO, so the question is there is some benefit to using only the prefix tuning for doing per user DPO.
I agree.
So like how bad is it as compared to LoRa?
I don't remember, but it's worse. I know that.
Yeah.
Yeah. And it's better than like just doing SFT, so it's still better to train it. But yeah, but that's a good question. I forgot about the exact numbers. Yeah. Okay, so I actually have a second part of the talk. Are people interested? I know it's like around 1 p.m. I thought that the time is like 1 hour, but okay, so I'll continue. And if you need to leave, please feel free to leave.
Well, maybe you could go like,
Like really fast.
like 5 to 10 minutes.
Okay, sounds good. Then yeah, I'll do that. So yeah, now the question is, I told you a bunch of ways to do personalized language model, and under this preference optimization framework. So the question is actually doing preference optimization as it is a good idea? And in particular, right now, all the preference optimization is done through a margin-based loss. So what do I mean by that? So recall that the DPO loss is basically some function of the log probability of the chosen response minus some function of the log probability of the rejected response. Similarly, for reward model as well, we are having this margin between the reward of the chosen response and the reward of the rejected response. And it turns out that all these PO algorithms have similar forms. We can almost always write most of the star PO algorithm as a function of the chosen log probability minus a function of the rejected log probability, and then do some transformation. And then, so this regularizer is a lot of times now people add a negative log likelihood to ensure that the probability of the chosen response does not decrease too much. Okay, so a lot of time these PO algorithms take this form. So what we observe in training is that actually there's synchronized up and downs during the training trajectory. So this is evaluated on the TLDR data set I mentioned before with the real preference. And then with DPO algorithm, and this is the training trajectory for Mistra 7B, and then the training trajectory for Llama 3AB. So the log probability of the chosen is the red line, and the log probability of the rejected is the blue line. And you can see that there's actually perfect synchronization between them. And when we observe this seems a little bit weird. And then we also look at it for even more models, Llama 3.23b, and then also like Gamma 2, yeah. So Google's model and Facebook's model and Mistra's model. So turns out that across multiple data set, and later on we will see actually across all star PO algorithm, we observe these synchronized updates. So why is this the case? But before we answer why this is the case, we should probably first ask ourselves, is this even something we need to worry about? It turns out that yes, it is in some settings. The main reason actually why this happened is because the margin-based laws fundamentally underspecify the behavior of the individual term. So we don't really specify the behavior of the log probability of the chosen and the log probability of the rejected. And because of this, there are several consequences. The first one is in safety-related alignment tasks, what we want is we want the probability of the rejected response to decrease, hopefully never happen. But because of the synchronized update, we can see that sometimes the probability of the rejected response overall is actually increased over time. And then the second setting is even if the rejected log probability is decreasing, these synchronized updates almost always imply that the chosen probability will decrease at the same time. So why is that a problem setting? So in settings where the chosen probability, the chosen responses are ideal responses, and in particular, in a lot of cases when we do like these DPO training, the chosen responses are now demonstration data. And then we generate rejected responses on policy. So in these cases, these chosen responses are super ideal. So we want to maintain or at least increase the log probability of them. But because of these synchronized updates in training, we can see that this is not happening. Actually, the chosen response log probability is decreasing over time. Okay, so as a side note, in settings where we only have on-policy preference data, meaning that we don't really know, and in this case, we don't really know whether we want the chosen and the rejected response to like behave in a certain way. So in those cases, then the ideal behavior is unclear, so maybe this is not problematic. But in a lot of cases, when we train with demonstration data, this will be a problematic thing. So why something like this is happening in all the algorithm we've seen. So let's just take DPO as a case study, as an example, and I will just use 2 minutes to go over this and we can end very soon. Okay, so I have the DPO loss for a particular sample is like this. Okay, and then, the shorthand we will use is log pi w, which is the log probability of the chosen response, and log pi l, which is the log probability of the rejected response. So it turns out that if we use first order approximation, we can see that the change in the chosen log probability depends not just on the chosen log probabilities gradient, it depends on both of the gradient. It depends on both the chosen gradient and then the rejected gradient. Similarly, the change in the log probability of the rejected depends on both the chosen and the rejected gradient. And this is a direct consequence of this underspecification in the objective. So why is that the case? I think to this audience probably it's very obvious. So yeah, we can get the gradient of the DPO, and then we can just use first order Taylor approximation to get that the change depends on the inner product. So yeah, so the first takeaway is current preference optimization objective, margin-based preference optimization objective have this gradient entanglement effect we call, which is individual log probability depends on both gradients. And so what does this say? It basically says that there's only one case where we will have the chosen log probability increase and rejected log probability decrease, which is when the inner product of the gradient is less than or equal to the minimum of individual gradients squared. And this is unlikely actually in language model case because when we profile the inner product gradients, they're really large. And in particular, when it's in between any of these two gradient norms squared, we will always observe the synchronized up and downs. Okay, and this is seen in all kinds of algorithms, not just DPO, but all these PO. And okay, and then like depending on different conditions, actually, the requirement for this inner product can be lenient or not for us to determine whether the synchronized update will happen. And then because of this, we have some like algorithmic suggestions. And then the second takeaway, actually, the second takeaway is that the inner product of these responses, a gradient of these responses depends on individual tokens gradient inner product. But for individual token, gradient inner product, it can be negative, it can be very small. So maybe one algorithmic idea is to pick out those tokens that are significant, that give us these negative gradient inner products. But in general, the takeaway is margin-based preference optimization. If you know your chosen response are demonstration data, it's probably not a good idea to do it naively. So lastly, yeah, we are just starting as a lab, and then there's a lot of interesting questions we're investigating for mainly trying to be providing more controllability and reliability for modern AI system, but also trying to fulfill our curiosity. And on the fundamental side, we're trying to understand what are some insights that are transferable between small and large models. So scaling law is an example, but is there some other things that we can do, and what's the basis for scaling laws? The second thing is, I think some people may be interested in like effects of architectures on the learnability of data problems that we care about. So forget about computational efficiency related issues for different architectures. Is there some fundamental limits when we are modeling natural language distributions? And then capability focused. Right now we're looking into like preference, reasoning related tasks, and then it will be like RL focused related projects. And then like I presented at the beginning, we also have like different human-centered personalization related questions. Yeah, and then if you want to chat about research, please let me know. Yeah.